Hi, in this video we will show how the recently derived, the previous video, Bohr-Sommerfeld rules can help us showing that the so-called wave-like phenomenon can be interpreted in terms of a corpuscular approach, in terms of particles. Let us see how that can be done. First, let's begin with an account of duality. We know that in quantum mechanics we have a number of phenomena that can be interpreted in terms of particles. We have black body radiation, when the field is expressed as an infinity of harmonic oscillators. We have the photoelectric effect, which is clearly interpreted in terms of particles, both for the electrons and the field, the electromagnetic field. This is the same with the Compton effect, when the field and the photons, in terms of the photons, and the recoiling electron are both interpreted in terms of particles, and we use a special relativity to make the balance of the momentum, of the momenta of the two entities, and also cloud chambers, in which we can see a track that will be clearly related to particle behavior. Of course, these are but an example, not extensive example of phenomena that are related to a corpuscular interpretation, but they are clearly the most common ones. But we also have some phenomena that can be interpreted, this is what is assumed, only in terms of waves. These are the phenomena that are generally involve interference and diffraction. So, for instance, we have Bragg's law, which is related to an X-ray that is reflected by a crystal. And we also have double slit interference. These are also two examples of a number of other phenomena that can be, as it is assumed, interpreted only in terms of interference and diffraction. What is our interest here is to show that these phenomena, which can be related to interference and diffraction of waves, can also be interpreted in terms of particles if we understand that they always are related to a sort of symmetry, and thus can be formalized, mathematically formalized in terms of the Bohr-Sommerfeld rules. So the Bohr-Sommerfeld rules will be the key to understand that these phenomena can also be interpreted in terms of particles. Let us see first with Bragg law of diffraction. Okay, in this case we will assume that the incoming radiation is constituted by photons. So we are assuming that these are particles, and that the crystal has a Z symmetry. So just to be simpler, Z symmetry, which reflects the way the symmetry planes of the crystal are separated. In this case, we are having this symmetry in the Z direction, we automatically have, as we have seen in the previous video, Bohr-Sommerfeld rule related with the symmetry and the momentum that can be transferred to the crystal. What the Bohr-Sommerfeld rule says is that this momentum can be transferred only in quantized way. Indeed, if we make this integral can be easily done. We have that the change of momentum, the momentum that is transferred to the crystal or taken from it, can be done only in terms of integral numbers. This automatically let us make the connection between the incoming moment and the moment transfer. The moment transfer to the crystal is given by delta pz, and the incoming moment, of course, is the moment of the photons. So, if we assume that, we can rewrite this expression in terms of the quantum number nz, and this will be the account that the corpuscular approach can be done. But we can go further and we can relate this account, corpuscular account, with the Wavelike one. To do that, we may write the incoming particles, the photon momentum, as this expression, and if we do so, we end up with exactly the same expression we have for the Bragg law diffraction pattern, written in terms of undulatory descriptors. So the same thing we have here. This is completely equivalent to this, if of course we use this expression. And we can do that by using this expression. So this expression takes the corpuscular account into the Wavelike account. One may say, of course, that this is the nucleus, the core of the duality interpretation. At this point, we can, of course, not solve this issue, but we can assume that this lambda here is a descriptor, of course, of the momenta of the incoming particles, which are the photons, and it is an account of the collection of photons. That is to say that it refers not to a single photon, but to the ensemble of photons that constitute the electromagnetic radiation. But this is only, for the moment, only an idea that has to be formalized in mathematical terms. It cannot be assumed as an explanation for the moment. So, of course, we could have kept ourselves only in this point without making any kind of resource to Wavelike descriptors, and we will have the same account of the diffraction pattern that's found on the detectors. Okay, what is we have just done to Bragg law diffraction can be repeated to any so-called wave-like phenomenon. For instance, if we have a double slit interference and diffraction, we have both phenomena here. We can assume that because of the symmetry of the problem, we may have the probability amplitude in the center of the slits as equal. This means this symmetry means this equation here, as we know because of the previous video. And we can also assume that at these points we are putting our coordinate system here in the center. We have the same situation, which is represented here. If we do that, it can be shown that the interaction of the photons with the slits will give us exactly the interference and diffraction patterns by means only of the assumption that momentum is transferred between the incoming photons and the slits in a quantized way. Then this is the important concept here is of course interaction. If we are talking about particles, we need to talk about interaction, and the interaction is related to the size of the slits and the velocity of the incoming particle. This, of course, can be electromagnetic field, but can also be electrons or atoms. And the size of the slits is related not only to the size of the slits is related to the velocity of the particles, because particles with high velocity, if the velocity is high, it means that the particles will pass very quickly in a very short period of time through the slits, and this means that the interaction will be lowered, and so the phenomenon of interaction will be lowered too. If this can be understood in terms of wave descriptors by saying that if the velocity of the incoming particles is high, then the lambda of the ensemble, because we are talking about the ensemble of particles, the lambda of the ensemble will be low, and then the slits will have to be very small to make the interference and diffraction pattern to appear. So the same way we can understand the problem in terms of waves, we also can understand it in terms of particles. In the case of particles, of course, we have to make resource to the issue of velocity and relate it to the size of the slits. In the Wavelike approach, we make the same thing but using the descriptor, which is a Wavelike descriptor, is the length, the wavelength. But then this is the way we can make an interpretation, corpuscular interpretation of any Wavelike phenomenon. It is natural to ask what happens If, for instance, I put a, a wall here to cover these slits, of course, when I do that, I break the symmetry. And if I break the symmetry, I obviously cannot use Bohr-Sommerfeld approach anymore. And thus, since the diffraction and interference patterns comes from the application of these rules to the phenomenon, and I cannot apply them anymore, the diffraction pattern will and the interference pattern will disappear. This is the way we can understand all these kind of so-called wave-like phenomena in terms of corpuscular behavior. This is what we would like to say, for instance, and for the time being, we will come back to these issues later on with more mathematics done. In the next video, we will talking about the Feynman path integral approach, which is just uh, an extension of what we have already done to find the Bohr-Sommerfeld rules. Thank you for watching.